My name is Gil Montembo. I'm the team lead for Project 13, the Operational Sequence Designer. This is a project sponsored by Mike Kalos over at Newick. Now, to my right here is Nate Long. He is our Scrum Master. To my left is Luke Machado and Jeff Bentz. They were both developers on this project, and I'm going to leave it to Jeff to explain what an operational sequence is.
All right, so okay, before getting into this, it is important to address what an operational sequence is supposed to be. It's defined as a means of visualizing relationships within a combat system, those relationships being between individual weapons and the system as a whole. Newick currently implements operational sequences as a measure to ensure safe launches, where the sequence evaluates whether all launch requirements have been met, and then notifies the system of a success or a failure without, of course, without the missile or the weapon actually having been launched. Sorry. And for the sake of simplicity, we're going to define a sequence right now in just a very general way as a series of steps used to complete an action. And since most of us don't have any intimate knowledge of how these combat systems work, we wanted to develop a simple example using a simplified version of an internal combustion engine. So for this engine to fire properly, it needs three components, those being fuel, air, and spark. If the air to fuel ratio is within an acceptable range and there's a spark present, the engine will fire. If any of these components are missing or that ratio is outside of that range, a misfire will occur. And the operational sequence approach to this problem would be able to check all of these components beforehand, notify the sequence, notify the system if anything goes wrong or if it's going to be successful, and then most importantly is able to reevaluate the sequence in the case that any of these variables are changed at any point. So currently at Newick, operational sequences are developed by being hard-coded by programmers. This requires extensive knowledge of C++ as well as knowledge of how the combat system works and also knowledge of the weapon to be implemented. They need a new solution for this in order to minimize the time it takes to develop and train and integrate. So the proposed solution for this problem is the Operational Sequence Designer. It's a standalone application that uses an interface that allows users to visually create sequences through diagrams. It's usable without any knowledge, well, with limited knowledge of C++ or programming, and can be integrated easily because as it stands right now, in order to integrate the weapon into the system, there needs to be somebody with the knowledge of what needs to be implemented and then also somebody who understands code and the combat system. These people need to be in the same place at the same time or need to be in close communication in order to develop this. Where using the software and not needing to know code, the subject matter expert in charge of understanding the weapon to be integrated can themselves design this sequence, send it off to a software developer who can then integrate it into the system, effectively making these two parties in this process independent of each other. Now, the designer uses a node-based system for design where a node represents either a value or operations that are performed on a value. These include comparison operators and or not, and mathematical operators, adding values, subtracting values. Pins that act as a means of entry and exit from a node, so data can be sent to the node and be sent out of the node, input and output. And as well as connections, which are just responsible for propagating data between pins. As mentioned before, the software is usable without very extensive knowledge of programming. That's because the program itself generates a C++ header file, which can then be easily integrated with how it's generated in a standardized way, integrated into the combat system. This file includes just simple user structure definitions, all of the nodes within the sequence, signals and slots that are used to connect into and out of the sequence using Qt signals and slots, which is the IDE that you typically code in. And exposed variable references, or exposed variable references, which are used, they can be modified by users, and a global sequence variable that's just used to reference the entire sequence as a whole for developers. To develop this project, we use C++ in Qt Creator with QCustomPlot, which is a library for plotting and graphing that we modified into a diagram editor, and also GitHub for version control. And now with all that being said, Nate and Kevin are going to take you through the process of creating an operational sequence.
All right, so as Jeff mentioned, we are going to be making a quick sequence that demonstrates the basically modeling a internal combustion engine. So we are greeted with this screen right when we open up a program. We have two options. We can either start a new project or we can open an existing project. For this example, we are going to start a new project. We're just going to call it engine. And this is going to make a new sequence diagram, and that's what we can see right here in the middle. We have a list of nodes that we can select from down on the left. Now, I'm not going to go through each one of these, but these can be implemented into the program later or removed. This is kind of an experimental project, so these nodes can be kind of tailored to fit the needs of whoever's going to be using it at Newark. So going back to our engine example, we require kind of three initial parameters that are going to be used as data entry into our sequence. As a reminder, those are going to be the fuel volume, the air volume, and that spark. So we need ways to get those values from an external program into our sequence. For that, we're going to use these variable nodes. Now, as Jeff mentioned, these variable nodes are going to be available in that operational sequence header, so the control system is able to modify these values, and our sequence is able to pick up on those modifications and immediately act on them. So we made three new variables here. We're going to name them fuel volume, air volume, and spark. Once we do that, we are going to be setting their data types. So all variables are going to need data types. Our system has a couple of data types that are baked right into it. Those are going to be ints, floating point numbers, booleans, that kind of thing, your standard C++ data types. But we also have support for user-defined data types, so things like structures. So the system is flexible in that we can have data types that the user defines, and we're not limited by just what the sequence can do by default. So we've made these three variables. We finished. The top two are set to doubles, just floating point numbers, and the bottom one, the spark, is going to be set to a boolean. There either is a spark or it isn't. So that concludes kind of our data entry portion. Now what we can do is we can start actually manipulating these variables to see, so this would be the sequence aspect of it, to see if the ideal circumstances for combustion are present. First thing we're going to need to do is we're going to need to calculate the optimal air-to-fuel volume ratio. So for that, we need to divide the air volume by the fuel volume. We're going to use a divide node for that. Now, in order to utilize the division on these two input variables, we need to somehow link them. We're going to use that by the connections that Jeff mentioned earlier. So we connect the second pin of all the variables, the two variable nodes that we're going to be dividing, into the divide node. And we can see how the color changed on the inputs of the divide node. That just indicates that the division is going to be a floating point division, and that's important. So now we have that. The output of that division node is going to be the resulting division of those two values, and we can use that to compare to an optimal value. In this circumstance, the optimal value, the optimal air-to-fuel volume ratio, is going to be 14.7. So we need some way to actually verify that the output of that division node is, at least in this case, exactly 14.7. So how we're going to do that is we need to include the value 14.7 somehow. So we're going to make a new variable node. We're going to set its default value to 14.7, and then we're going to change it to a constant. Now what that means is no external program can modify that value. It's a static variable. Once we have that in there, we can compare the output of the division to that 14.7 value. We're going to use that with, we're going to do that by using a equal node. Similarly to the divide node, we're going to click and drag some connections into the equal node, and now the output of that is going to be a Boolean value, true or false, whether or not the air-to-fuel volume ratio is that optimal value that we said earlier. Now, this is not enough for combustion. We still need the spark. So we need to make sure that the volume, or the ratio, is optimal and that there's a spark present. So for that, we're going to use an AND node. Similarly, connect them up, and the output of that AND node is going to be a true or false value, representing whether or not the ideal conditions for combustion are present. So at this point, the kind of logic aspect of the sequence is done. Now we need a way to extract those values. Now, for a control system, it would be real beneficial to have a an indicator of if any of these variables change, if the ideal conditions for combustion are met, and they aren't. So both of those conditions should alert the control sequence or whatever program this sequence is housed in. So for that, we're going to use a branch node. Branch nodes act kind of like if statements, where the second input pin is going to be a true or false value, and that true or false value determines which output pin the branch node is going to signal on. You see that there are two output pins there. The Boolean gets dragged into the middle, but now the bottom pin. But now this kind of raises the issue of when does this branch get evaluated, or when should we check? Now it's reasonable that this branch shouldn't be checked continuously. It should really only be checked when the variables, any of the input variables, are changed. So what we did is we implemented a system of kind of control flow in our diagram, which allows us to kind of specify what times these actions will occur, so that every one of those variables has an unused pin right now. That pin is going to fire every single time any of those variables are modified. So, as I mentioned earlier, that would be a real good time to try to reevaluate that branch statement. So, we're going to be doing that. We're going to do that by connecting those call pins together, and now the output of that branch is going to be on the first pin anytime any of the variables change and the optimal conditions for combustion are met, and the bottom pin otherwise. Now is the actually communicating with the control system. For this, there's a couple ways we can do it. We can use signals, which are kind of a Qt implementation to signal a higher program. In this case, we are going to use what we call green nodes. And this is just for demonstration purposes. What that's going to let us do is those green nodes integrate with a secondary program that we made that allows a user to view the state of the sequence diagram as it executes. So this one green node is going to appear as a single green box in this secondary program, and is going to light up whatever color we choose based on the output of this branch node. So we can specify two colors for that new node. We can have the default to be red, and then the secondary color to be green. And if the output of the branch is the first pin, a success, we can set the color to green, and if it's not, we can set it back to red. So at this point, we have our full sequence diagram. It's pretty much complete. Now what we can do is we can hop over to the green board modifier. Now this is going to let us lay out all of those green nodes. We only have one in this particular sequence. This is a pretty simple sequence, so we only have one, but we can place it there, and it's going to show up in this layout in that secondary program. And we're going to show you how a kind of more complicated program would look. So we're going to open an existing project. Now what this is logically, this is the exact same program that we just made, except now we are including many more of those green nodes. So we can see that there are 5 now instead of just the 1. Now if we go over to the green board tab, we can see that the layout that we've been able to establish the layout of how those green nodes are going to appear in that secondary green board program. Now if we go back to the operational sequence, a quick note I want to make is before we open that secondary program, right at the top there we have a new node, a delay node. Now that works to delay that call flow that I talked about earlier. So basically how that works is the variable node, or one of the variable nodes is going to change. It's going to trigger that green node at the top there to change to green, and then a short delay later, it's going to set it back to red. Now in our green board program, that's just going to blink, indicating that that variable was changed. So this is that diagram that we made. Now we can open up the green board program and start running it. This is the green board program. Again, this is an optional secondary program that allows a user to just view the execution of the sequence as it goes. This is not required for the sequence to operate. An important aspect of this program was to be able to kind of separate the visual aspects of the diagram and the logical aspects. So the logical aspects can run completely independently of the visuals if necessary. In this particular instance, we want the variables, we want the visuals, so that they are. And then you can also see in the bottom right here, since we are not actually going to be putting this into a control system, we need some way of modifying those variables manually ourselves. So we made this kind of third program just to allow us to modify those by hand. So we have those three input variables, those three input arguments that I was talking about earlier, and we are able to modify them by hand here. So right at the top is the fuel volume value. We can set that to 147, and you will note when we update that value, the fuel volume change green node will blink. Again, that's kind of the functionality that I was talking about earlier. And then anytime any of those values update, the corresponding green node will blink. Now we can set the air volume to 10. You guys remember, the optimal the air volume ratio was 14.7, so 147 divided by 10 is going to be that optimal value. So once we update it, we can see that the green node corresponding to whether the fuel volume is optimal or not lights up. So it is. So now we can carry on. Now the one thing we're missing is the spark. It's set to false right now. We can set it to true. We update that variable, and now we see the final node will fire, indicating that all the proper arguments are set for the ideal conditions for combustion. Now, if we go back and change any of these variables, the sequence isn't done. Obviously, this is a running sequence. Things could be modified, things could change as it's run. So if we change any of these again, it's going to update, and this updates again anytime any of these variable nodes are changed. Just as a note, there are other ways for an external program to integrate into the sequence. We mentioned the idea of signals, where our sequence can signal a higher program. But there we also have slots, the idea of slots, where we can have just kind of empty spaces in our program that other programs can link into, or our control system can link into. Now with that, that concludes our demo, and I would like to open for any questions.
So, number one, thank you for the brief of the project. So, how scalable is the solution? Have you looked at how many nodes you can apply? What's reasonable visually? And then what happens when you kind of get to a full screen? Can you drill down into different levels?
So the idea of levels was something we touched upon earlier, or we looked at earlier in our development, because this is kind of, or the program is kind of simulating a more kind of graphical programming language, so it would be nice to implement something that allows kind of use of something like functions. We did have that implemented a little earlier, but with time constraints we decided to kind of put it out for the final project. But there was an idea of sort of clustering where you could take a cluster of nodes and then make them its own custom node type that would show up on that bank, and then you could use it just like any normal node. So that's somewhere where this project could go later on. As far as scalability, that would certainly help to cut down on the visual clutter of one of these diagrams. Obviously, even with that simple diagram, it was getting a little complicated, so that would be a situation where you want to shrink it down a bit. Performance-wise, there's the back end is extremely light as far as how these nodes actually interact with each other while it's running. It's extremely light, so I don't see any problems with performance while it's running. And then again, the visuals extremely light. The editor is extremely light, so I see it being pretty largely expandable in that sense.
How about now integration into a bigger system? So you kind of have that laid up on a particular background or white background or whatever. We're integrating that into the system. Can you kind of layer that on top of another display or?
Oh yeah, surely. So that display that we made, it's just a simple kind of it's a Q widget. So I know they use Qt, or the system use Qt for like visuals. So it's really easy to take that, plop it in somewhere else. As far as where the diagrams are being stored is again in that header file. Really simple format, so even if you didn't want to use what we did, the generated header file is really simple to parse. It's really easy to parse these visuals back out. So if you didn't like the program, it's pretty easy to customize it.
Are you able to take any of the output pins and then drag them out to multiple input pins, or does that use them?
No, so every input pin can only accept one connection, but every output pin can accept many connections. So as we saw with that sequence diagram, every one of those variables was being used multiple times for multiple inputs. If there's no more questions, thank you very much.